All right. So we have talked about the mean and variance, right? We know the mean and variance of normal whenever we're writing a normal distribution here is mean is mu, variance sigma squared. Okay, and we show the density to you as well. So now it is very important actually, and both of them are required, how to derive the mean and variance of a normal random variable. Okay, and for us, we're gonna walk with you the details, but also the textbook has two examples of one example, I think, on page 189, showing you the steps of how to do the derivation as well. Okay, but because it's important, not only because the results are important, but also it gives us really good practice of doing integration. Okay, like I said, this is part of the review of the course, so I would like to take the time to go over it carefully. Okay. Alrighty, so if x follows a normal distribution mu sigma squared, okay, then if we define a new random variable here, okay, we're doing some transformation of it. We're doing x minus mu divided by sigma, okay. This is a new random variable, so we use capital Z, okay, use a capital letter and I use Z over here. Then Z has a standard normal distribution, meaning that Z is gonna follow a normal distribution with mean 0 and standard deviation or variance 1. Okay, so we're gonna see later why if x follows a normal mu sigma squared, then z follows a standard normal. We're gonna see why towards the end of this part of the lecture. But for now, we're gonna actually use this fact to show the mean of a normal is mu, and then the mean of a standard deviation, mean of a normal is standard sigma squared. Okay, and for us, so just to get started, let's first start with showing the expectation of x is mu. Okay, this is required, meaning that you need to know how to do it. Okay, all right. So what this is showing, the reason why I'm bringing up this standard normal distribution is because, like I said, if we know this and know this, so this is true. So pretty much it boils down that how are we going to show that the standard normal distribution, the mean is 0. Okay. So the standard normal, just so you know, when means, okay, so you know it's negative infinity to positive infinity, right? I'm just writing, oh, let me actually do that. That is probably better. I just want to write the PDF, okay? So FZ, okay? Let me use Z down here. So this is showing the PDF of Z, okay? The PDF of Z, as we can see over here, should be 1 over 2 pi, because sigma square is 1, okay? And the E to the, so here is 2 because sigma square is 1 again, so it's 2 sigma squared down here, so it's only 2. And then up here is z squared because it's z minus 0, which is squared. Okay, so this is the PDF of a standard normal. Okay, and that's what we're going to use throughout to show the expectation of z, which is 0. Okay, so let's continue. Okay, like I said, since they are equivalent, so it's sufficient to show the mean and variance of standard normal as 0 and 1. So here we're trying to show that expectation of z is 0, okay, using the fact that we have the PDF of z. Okay, all right, so I'm going to show the result together, but I'm going to walk you through so it's easier instead of me writing it all of the notes down here. And okay, so expectation of z, okay, we know it's going to be about, so here that's why I'm using the PDF with a subscript capital Z to represent the PDF of Z. Okay, I'm using x as a like dummy variable, so don't worry about whatever it is. But what important it is that it's the expectation about z, right? So I need to use the PDF of z. Okay, I'm using x as the dummy variable, and we know that it's talking about the expectation. So if you remember, expectation of x, right? Just generically for a numerical for a continuous random variable, we know that it's x f x dx. Okay. So what I'm doing over here is that everything is about z, but I'm using x as a dummy variable just to avoid like all of the complication. So we have fz x, right? So x, fz x, and then dx. This is directly by the definition of the expectation. Okay. All right. And from there on, we know that the fz function, right? The PDF of z is all of this whole thing. So I'm plugging that in. Okay. So this is x fz dx. Okay, and one thing we always try to do, as you can see here, is that this whole part is constant with respect to x, right? So the integral is about x, so I can always bring that out, just like this step over here, okay? Then we have this particular integral. Okay, so as a review, okay, if you look at this, okay, well, in this case, it's easy to observe directly, but you can always do integration by parts, okay? And I will introduce the integration by parts when we're gonna show the variance of x equals to sigma squared. But here it's pretty straightforward to recognize to some degree that the integral is this, okay? All right. And then of course the constant, the integral is this with minus in the front. Okay, so then the constant is in front, and then we're integrating from negative infinity to positive infinity because that's what the integral range goes. And this whole thing, as you can see, because it's x squared and they're the same when you're taking sigma square and negative sigma square. So this whole thing goes to 0, meaning that we have shown that the expectation of z is 0. Okay, so this is pretty detailed, like I said. But for us, it's very important to, first of all, recognize the PDF of Z. Okay, so you should write it out, like according to the normal density, like plug in the mu and sigma square over there. And then, of course, it's important to recognize that this is about the expectation of Z. So we're using the PDF of Z, okay, even though we're using X as dummy variable over here, okay. And lastly, okay, is how to do the integral, okay. So this is review going back to Math 127 or AP Calculus BC, I guess 126, yeah, Math 126 and then AP Calculus AB, okay. All right, so the mean is relatively easy to do. So now let's go to the variance, which is where I'm gonna show you in some places you do need to do integration by parts in order to finish the integral, okay. So the expectation we have shown of Z is 0, okay. And then here, we're asked to do variance of x equals to sigma squared, so it's the same as we're saying here. It's the same as showing variance of z is 1. Okay. Alrighty. So variance of z, as we know, okay, is expectation of x squared, right, minus the square of expectation. Okay. So this one is 0, okay, given, oh, sorry, let me use C everywhere so I don't get confused. Okay, you see how easy it is to get confused? So this is 0, okay, so this term goes away. So pretty much we need to we need to show the expectation of Z squared, okay? So expectation of Z squared, so let me actually show the results here and then walk you through, okay? The variance, okay, of z is expectation of x z squared minus square of z expectation of z, and we know that this is 0, so it becomes this. Okay, so this, okay, it's a function, right? We're looking at expectation of a function of a random variable. Okay, and we know that, well, function is x squared. Again, the PDF is about z. Okay, so you have fz over here and dx. Okay, so this is what I was saying. If I'm looking at a function of a random variable, right? So it is the same as doing this. Okay, so this is exactly what we're doing over here, except we highlight that the PDF is about z, okay? And then x is a dummy variable over here. Okay, then we come to this part. Okay, it's very similar to before, like the variant expectation, remember, like this is only 1. Okay, so, and then we recognize it immediately that we're able to maybe without doing the integration by parts. But this one, this is the case that we do need to do it. Okay, so first of all, I bring this out because it's a constant. Okay, and then we come to here. Okay, so integration by parts, just to refresh your memory, and this is also posted on Moodle under the other material at the bottom, where I have a calculus review document. Okay, so integration by parts says that if I have integration of u dv, okay, that's equivalent of evaluating u times v minus integral of v du. Okay, all right. So for us, it does take practice and then maybe try and error to some degree to figure out what is your u, what is your v. Okay, so here we're actually going to use u to be x and then dv to be the remaining. Okay, so yeah, right. So x squared. Yeah, so here we're using x, okay, and then so if you look at this, u times dv is whatever we need to do over here. Okay, alrighty. So oops, I will just add a little bit more detail over here. that, okay, one second, okay. That, okay, so like I said, if I have u to be x, okay, and dv is x, e to the negative x squared divided by 2, then we know that du, okay, is the same as dx, okay, and v, as we can see, is this is what we actually did from the expectation part. I think v here will just become, let's see, x equals to, yeah, I think du is dx, and then v will be negative e to the negative x squared divided by 2. Okay. All right. So this is required, like say you need all of these pieces together, right, in order to do the integration by parts. So really quickly, we know that u dv, right, is u times v to minus v du, right? Okay. So for us, we're able to, from the second line to the third line by doing this integration by parts formula. Okay, so here, this is the part about v times u times v. Okay, this is the part about negative, yeah, negative, but then there's a negative sign, so it's a plus, and this is v du. Okay, once you have u, dv, du, and v all ready, then you're able to do this part. Okay, and then lastly, this whole thing is 0 once you look at it, and then this part, as you can see, okay, together with 1 over 2 pi squared, okay, 2 pi, that's what the constant in front of it. If you look at this, this is exactly integral, right? Integral of the normal PDF, the standard normal PDF. Okay, so that's what this is about. So if you remember what I wrote earlier. Okay, so this is e to the negative 2, right? And then z squared. Okay, so we know that for this, for any normal distribution, right, if you integrate it over the entire real line, by definition, it integrates to 1 because it's well defined. So that's why we can pretty straightforwardly, once we recognize this, the inner part, right, this part is the PDF, right, of standard normal, and then we're integrating it on the real line. So we know that it's going to be 1. And that suffices to show, right, like we're saying, so this is to say that the variance of z is 1, and then that is equivalent to the variance of x is sigma squared. Okay, so like I said, not easy, definitely not easy, and then it requires a lot of the new knowledge, like say the variant, the expectation, like all of this results, right, and then also the expectation of a function of a random variable, right, and then of course the z and x, all of the different pieces, and lastly, it's a review from before of integration by parts. Okay, so you need all of this in place to be able to realize or to show certain properties of the normal distribution. So I really highly recommend you to either sit down, doing the steps by yourself carefully, and if it's really challenging, textbook page 189 gives a good flow showing the expectation and variance for the normal. So you can check that out as well, and reach out whenever you have questions.